Yeah. So today the big item is Devon presenting the new documentation for the discretized package. But before we dive into that, is there like any 60-second points that people want to talk about first? Vaid?
Oh.
No.
Nothing particular on my end.
I think from my end, the big lesson from South Africa is that we really need to have an offline installer for everything, because the whole depending on Anaconda and downloading it never works. It's always so hard.
Yeah.
I think Docker kind of the solution. Do you know, Saga? You probably looked into it before, eh?
I think that could be a good solution. I think, and especially if you want to, I don't know, like depending upon the way, like if you're using Binder or Azure or whatever cloud platform, I mean that's okay. But if you really want to install their own machine, I don't know. I'm not sure what's the best way. It's tricky.
It is.
Yeah, even well maintained package, it's actually tricky, right? Like a lot of like other packages. So yeah, not 100% sure.
Yeah. For instance, like now NumPy is. We need to downgrade NumPy to be able to run discretize.
Oh, I see.
Compile it. Like all of this is getting a nightmarish. It would be nice if we could just like freeze all the versions, and then.
So actually, we before we kind of get down to Devin's tutorial, I met Lindsay last week with Fernando Perez. They were coming here. Well, Fernando was giving a talk with actually one of them is a developer who made the Python named Guido. I didn't know that, but anyway, they gave a talk, which was interesting, just like kind of cloak one. But by the way, what we were talking with Fernando was having a project between Stanford and Berkeley, having some sort of like a cloud-based platform in terms of data management and whatever, running the simulation. So like a Pangeo project. But I think that's probably way to go. And it seems like if you have some sort of cloud, suppose we have money to buy a cloud, then like that seems like not a big deal. But not 100% sure.
Yeah, I don't know, man, because of course if you're on the West Coast, you guys all have fiber, but as soon as you go to like emerging markets, being online is not an option.
Right. So you definitely need to install in their machine.
Yeah.
Right.
Done? Yeah. One point, like we don't need to downgrade NumPy to work with discretize. That was something else. It's
GeoSci.
If you work with GeoSci, the GeoSci have the problem. So that was a problem with Nick. And the thing is that for Nick, the problem was that he's on Windows, so he's using the pre-compiled version, and he's installed discretized from pip. So it's a pre-compiled version that works with actually the newer version of NumPy. And he was trying to downgrade NumPy while working with a discretized version that was pre-compiled with the newer. So that was the whole issue of things.
Also, so pip has a few pre-compiled one too, eh?
But that's what we do with AppVeyor. We have to do that for Windows users. Otherwise, if they don't have the C compiler installed, it's not working for them. And it's not by default on Windows machines. So that's why we have to have this pre-compiled version. So we do ideally we do it with AppVeyor, but sometimes we break AppVeyor. So it's actually me doing it manually to upload that. But right now AppVeyor is working. But the thing in NumPy, that change was like a pretty core change, if I understand well. So you pre-compile with NumPy 1.16, you cannot use that pre-compiled version with NumPy 1.15, which GeoSoft was using.
And have you built the wheels on 3.6 or 3.7?
I think AppVeyor do both.
Okay.
But this one was a NumPy problem. But I mean, for us, if we work from our own directory like a clone, it's not an issue. It was only an issue for Nick because he was keep installing discretized. But if you work from a clone, it's not an issue.
Yeah, but if you're from a clone, then you need a full C++ Visual Studio thing.
Yeah, exactly. Like you're more responsible on how things work.
Right.
But yeah, that's like this NumPy update was, I think, fairly big, and it's just that GeoStuff has a bug with the new version. Like they're not.
Yes.
Yeah. Or like the old style is like having a virtual box, like a Linux box. You pre-install everything and then just provide. So that could work for Windows machines, which is a little bit easier. You could like like a virtual box, like you can have a Linux system on your Windows machine.
Oh.
So that like you can pre-install everything into a virtual box and then just wrap it up everything. So we can basically provide that as a zip file. Then you can download it and run it. So that's kind of old style, but kind of works.
Okay.
One way.
Sounds like a lot of installation on the user side, though, right? They need to.
No, I think you don't really need to do that many. Like it's like exe, so.
Is that
Yeah, execution. So you basically execute that file, and then you got a box, and then it's like a Linux-based system, basically. So you can run most of things there.
Okay. Yeah. We'll have to do this eventually.
Yeah.
All right, Dev, floor is yours, man.
All right. Yeah. So I think in doing these tutorials, I was just gonna do a little bit of a walkthrough. I guess we could go screen share.
Yeah, that's what I'm.
Yeah, I was gonna show you guys what I had, maybe get a few comments. The things that I sort of wanted to do was assume that they don't know anything. Don't assume they know any of the terminology. I really want the tutorials to be well commented, so I spent a lot of time easing people into the terminology and what we're doing. I wanted some practical examples because if they're practical, then they can sort of be adapted to a general workflow. And I want to eventually touch as much of the package as I possibly can. So yeah, I'll just shimmy over here.
I cannot move it further than that.
But yeah, I've got 3 sort of sets of tutorials right now. So we'll start off at mesh generation, kind of a first step for using this package. And then a little bit on the operators. So averaging and differential operators, like what are those? Some like how do we construct them? How do we apply them? And then sort of the last one that I wanted to do was sort of like a solve your own PDE. So now that we have all the building blocks, like making meshes and how do these inner product matrices things work, then eventually you're going to get to a point where you've got a PDE, it's got some boundary conditions, and then you're going to need to construct it. So how do you go through the steps of applying the finite volume approach and solving it and getting something out? So I've got a couple examples for that.
Nice.
So if we go into the mesh generation, Tappa. Because I'm super thorough, we have a little bit of a title page and the gallery gets generated here. I'd like to put tensor meshes in front of SIL meshes, but I gotta figure out how to change that in the conf file. But does anyone have any preference on which one to go to first, just to do the little walkthrough?
Tree.
Tree meshes it is. So yeah, we have a little bit of a definition here too. So this whole idea of them not knowing anything. So what is a mesh? Trying to really get them to understand, okay, what is going on? What are we about to show them? And yeah, so we'll start with the tree meshes. So we have a little bit of a spiel on like what it actually is, like a little bit of an introduction. We're going to demonstrate how to create some basic tree meshes in 2D and 3D, some strategies for local mesh refinement, how to plot the tree meshes, and how to extract some properties like the volume or what is the number of edges in X.
Right.
So how we create the tensor meshes, how we create these tree meshes, we first sort of define the base tensor mesh, and then we refine in certain areas. We have a few rules The number of base mesh cells needs to all be powers of 2. So really thoroughly going through how you would do all this. So yeah, so you'd first import the packages. So we have a basic example where we're going to make a quad tree mesh 2D. And we're going to go and define the highest level of discretization in a rectangular box.
Mm-hmm.
And so each step, right, we comment it. So the minimum cell width of the base mesh cells, the minimum cell width, the number of base mesh cells in X and Y. Then we define our domain and create the tree mesh, our instance of the tree mesh class. Then we go and define based on this box, and we end up getting a plot like this. So that's the most basic, straightforward example that you could possibly get. Now we've got sort of an intermediate example. So we're going to then do some mesh refinement based on topography. So we're gonna define some function, or you could go and import a topography file. And then you're gonna use surface. And then we also show off that you could use this radial mesh refinement strategy as well.
Yeah.
And we end up with something that looks like this.
Right. Hey, Dev, if I put x naught is equal to Cn, is it gonna work out?
Well, yeah, you'd have to shift. You'd have to shift those functions over, right? Yeah. So we do actually talk about that in, I think, the tensor mesh tutorial, where we talk about you could actually put in like your bottom southwest corner as values. We also say that there's some flags like C, N, and 0. So we actually talk about being able to do that as well.
Right.
And then I think in the tensor mesh example, because it's the first example, we sort of start with the general way that you could go and define this mesh. And then we do an example afterward where we say, oh, there's a couple little shorthand things that you could do if you want to save space and you want to get fancy. So yeah, you can define the bottom southwest corner as being numbers, or you could use those flags like C, N, O for shifting the mesh.
Okay.
We do actually have that in an example.
Right.
Okay. So then we have one about extracting mesh properties. So once a mesh is created, you may want to extract some properties. Here we demonstrate some of the things that you can pull out. So yeah, you could extract what's the location of the bottom west corner, because it's a 2D mesh, total number of mesh cells, the cell center locations, which cells lie on the boundary, the volume, and then now we're plotting the cell areas.
Nice.
So instead of doing plot grid, this is now plot image. And then to have a 3D example as well. So now we do a full 3D, everything we've shown on the page that we can do, extracting the mesh properties, the mesh refinement is now 3D points. And then we take a slice of the 3D and see that.
Nice.
So that's sort of the general flavor of these mesh tutorials.
Nice. That's great. That's great.
So if we don't have any questions on that, I mean, I did one for, tensor meshes. I did a full one for the SIL mesh. And
I guess I would have one comment, Dev.
Yeah.
Like for next time, if you could log the volume, do a log 10 on the volume, you'll have more, more range on the color, right?
Yeah.
And also, it would be nice if if you could hyperlink, for instance, the refine function, if it could be hyperlinked to the API so people can actually see the function. You know what I mean?
I thought about doing that, but there is many warnings and things that have not been addressed in auto generation of the API.
Oh, I see.
So there's a lot of warnings and a lot of errors still in the build of this website. And those need to be, I think, addressed before we start just adding a whole bunch of new stuff and getting too excited.
Okay. No, yeah, but we should figure it out because we definitely want to be able to click on the function and it takes us to the API. Or otherwise, it's kind of a one-way.
Yeah. Right.
Yeah.
Should just ask Lindsay to help you.
Yeah, and I've had some thoughts as well about putting references and links in these files so that you have these auto-generated links. Within the website, you could link to different parts of the website, but if you download it as a like an IPython notebook, then the syntax, like the RST syntax, that link won't generate, and you have sort of gibberish in the in the words, like in your markdown.
No, I would worry too much about it. I think the website should be linked, that's for sure.
But the log volume for sure, I thought, yeah, I wasn't sure if it was going to be, oh yeah, that's fine, or if somebody else was going to kind of mention it, but sounds like it'd be nice. So
not major.
Easy fix, makes me feel good about myself. But yeah, if you don't have any other questions about this, we can move on to the operators.
Yeah,
that should be pretty quick. So yeah, numerical solutions to differential equations using finite volume method require discrete operators. These include averaging and differential operators. Kind of give a little bit of a definition of what that actually means, right? We might need to average a quantity that lives on one part of the mesh to another part of the mesh, or carry out these differential operators. So we have one for averaging. So we're going to go how to construct and apply an averaging matrix, talk about some differences between averaging matrices in 1, 2, and 3D, what happens when you average a discontinuous function, and then talk a little bit about the transpose. And I'm definitely hoping I can hear a few comments on that because there's some details I think that are important. So import the packages. So we have an easy 1D example where we're just going to compute a scalar quantity on the nodes, 1D example. We're going to average it to cell centers, and then we're going to compute that function at cell centers as a way to validate the averaging is numerically accurate. So this is sort of it's a bit cut off and I got to fix it, but we have our sparse 1D our sparse representation of the 1D operator. The blue curve is evaluating this function at cell centers. The dots are averaging from centers to nodes, and then we have the absolute error. We find out that it's an accurate averaging if the mesh is small enough. So just kind of showing what we're able to do with that. Then we sort of talk about how there's more places where things can live in 1, 2, and 3D. So we get we average, I think it was like from faces to, I can't remember where it was. There we go, faces to centers in 1D. In 2D, we get a matrix that looks like this. And in 3D, we get a matrix that looks like this. For a tensor mesh, it would be different if it was a tree mesh. And then we do some things about, okay, what's the number of cells, the number of faces, the dimensions of this matrix, and the number of non-zero elements. And then when we do a discontinuous function, so for us, we do things like define a cell-centered model, and then we need to average to faces. Basically put kind of a model. And then this is what happens if you use the cell centers to faces operator. This is if we didn't have all of the averaging matrices. And because I made a uniform mesh, if I want to go what is it? If I want to go centers to nodes, I can take the averaging matrix from nodes to centers and take the transpose. But I think that only works if you have a uniform cells. If you start having padding cells or tree mesh, I don't think you're allowed to do that. Because I kind of played around with it, and I don't think that's possible. Because if it was true, so here's kind of a bit of an example. This is if I use a cell centers to faces averaging matrix, I get this. And if I use a cell centers or faces to centers and take the transpose, I get this. So we get the stuff. Yeah, the corners, that makes sense, because you're basically trying to take values that are outside of the mesh, and I discussed that in the tutorial. But everything on the inside is accurate.
Yeah.
But if you don't have a uniform cell size, I don't think you can do that transpose.
Why not though?
Yeah, you can still do it.
There's no dimensions in it.
Oh, well, the dimensions of it are fine, but I don't know. So that's where I was hoping you guys could maybe give me some insight.
Inside should be fine. I think there's no dimensions. Only thing is the boundary, like a cell to node, node to center. One is not well defined. Like a cell to face, face to cell is well defined, right? Like you don't need any boundary condition. But,
exactly.
Cell to face, you need to put some boundary condition, and we did. So that's the only change.
So we do discuss that, because you're effectively asking it to go and use values that are outside of the mesh, or basically assumes that everything outside is 0.
Right.
But from what you're telling me, this transpose, like if I have padding, if I'm using a tree mesh, then that transpose that works. Or does it work to, like, is it still a second order averaging? I think there's some.
If you're putting a right boundary condition, it should be still second order. So you're imposing a certain boundary condition when you're doing it. So, face to center, it should be a second order. Cell to face, if you're putting the right boundary condition, still should be second order.
Yeah, but that's not me generating a face to edges, a centers to edges averaging operator. That's me taking the edges to centers operator and taking the transpose of it.
Yeah, it's the same. You just need to add an extra matrix to account for the boundary cells, right?
Okay.
So you're imposing, in that case, you're imposing the boundary condition. So to make sure that the boundary condition is correct.
There's no dimensions in the averager, right? It's just 0.5.
Yeah, there's no dimensions.
So okay, yeah. Right, and then so moving to differential operators. So that'll load up. Basically, we want to do these operations. We're going to do some demonstrations, so how to construct and apply these. Talk a little bit about the mapping and dimensions. So you're going to apply some of these operators to maybe a scalar quantity, and you're going to get a vector quantity out of it. So where do things go? And some applications of that. Transpose again. So 1D example, we just did, we had this function, this blue function. Then we used basically a 1D gradient operator. So we took the derivative with respect to x, and that's what the dots are. And then we took the analytic derivative at the cell centers and compared it, and we find that it matches. So to try and validate the operator. Talk a little bit about mapping and dimensions, and just sort of like I didn't really figure out maybe a better way do this, but I decided to just kind of make the gradient, divergence, and curl operators in 3D and kind of plot them up so you could sort of see the relative sizes. I mean, I could have invented some functions and applied it, but this just seemed like a good way of sort of demonstrating what these actually were. They're sparse matrices. These are the dimensions they have.
Right.
And then printing it out. So there is some statements that say, okay, this is a gradient that goes from nodes to edges. And so there's the number of nodes, there's the number of edges, and lo and behold, there's the dimensions of the operator. Here's the number of non-zero elements. We do that kind of a thing. And then we do a 2D example. So we're going to, I'll just go down to the plots. So we've got some scalar function u that lives at cell centers. We're going to take the gradient of that to, I guess that was the gradient to faces, so I need to change that. And then, we'll show that this is the gradient of that function. Then we have a vector living on the faces, and we take the divergence of that, and we get this. And then we're going to have sort of a rotational field at the edges, and we take the curl of that, and this is what we get at cell centers, because it's a 2D example, right? So if we're going to go from edges to faces, well, that's just the cell centers in 2D. Right? You're taking the curl of a function that's dependent on y, you're just going to get the z component. That's why it's being plotted this way.
Yep.
So there's sort of those examples. Do you have any questions about that?
Looks good. It'll be nice that having one like an order test.
Okay.
Because that's how we're testing all the gradient operators. So if you can take a look at how we're testing, and there are testing examples. So maybe even just for 1D case, Rob, you can plot it up, but showing one order test example will be beneficial.
I thought about it, but it's a tutorial more for how to use it. So the statement of saying these are second order differential operators, I think is sufficient. Because that would be useful information to know, but we're supposed to have made the operators, and they should be correct. They just need to know how to use them and know kind of a bit about what they are.
Okay, fair enough.
I decided to leave that out.
Okay.
But I could add that statement too.
Sounds good.
Are the tests shown anywhere, Sug?
I think in the docs of not sure actually. That's a good question.
Because I totally get your point, Devon, but I think it's not a crazy idea because people that are really into discretization will want to see those tests. If you don't have them anywhere, then that could be a place to put them, right?
Really? Okay.
Yeah, I'm not like a one simple example, that 1D example, averaging operator, just do a test for that. Because you got all the things ready, right? You got analytic functions, and just need to do a test.
Okay.
I thought.
So then the last part is the solving PDEs. So any comments you want to give on this? I have a feeling it's 99% correct, but I would like to get that up to 100.
Okay.
These were sort of the 4 steps that I sort of thought if you were starting from scratch, you'd have your PDE. You'd want to formulate the problem and its boundary conditions. Then you would want to apply the weak formulation. So you take the inner product with this some test function, and then we're going to evaluate those inner products according to the finite volume method. And then we're going to construct and solve a final discretized system. And so some of those things that we're going to need to do is how to set the Dirichlet and Neumann boundary conditions. And we have some discretization for time-dependent PDEs. So this is sort of I know how everything works before this, and now I need to solve my particular problem. can they go through this kind of create your own process and be able to kind of customize, like solve their particular situation? So I decided to do Gauss's law of electrostatics and then the advection diffusion equation, because the operators we have kind of let me do this.
Okay.
So in all of these examples, yeah, we're going to state, we've got sort of a 2D charge distribution. We're going to have a couple of point charges. And then we're going to go and try and get the electric potential and then go and get the electric fields. So we start with Gauss's law and Faraday's law. And Faraday's law, because it's static, will let us write the electric field in terms of the scalar potential. And then we have our boundary condition, our Dirichlet boundary condition. We'll assume it's 0 at the boundaries. So we go and put it in the weak form. So we've got a scalar test function, and we have a, I guess this is a, on the faces. I think I put it on the faces. Yeah. We just got a homogeneous physical properties. There's going to be no charge buildup on boundaries. So E on the faces is fine. We're not violating any like natural boundary conditions of the cells. Yeah, and so then we do our finite volume approach by evaluating, we evaluate these inner products, and then we cancel out any of the terms. And we end up with a system that's this. Divergence gradient of the scalar potential equals -1 over epsilon naught times this charge density. And if we want the electric field, we just take the gradient after. So that seemed pretty straightforward. So we put a little charge distribution at -10 and one at 10 and 0. We create our mesh, create the system, define our right-hand side, and in the end, we get something that's like this. So we got a little positive charge density on the right and one little negative one on the left. We have positive potential near the positive charge, and then we see our electric fields go from positive to negative. So there's one example that shows the whole process of starting with your PDE, applying the weak formulation, applying finite volume, and then simplifying it to like a final discretized system, and then and showing how you could then solve it and create the whole thing with discretize.
That's nice, Devin. That's great.
Yeah, thank you. And the second one I did was the advection diffusion equation. So this one gets to be a little bit fancy because it's got a divergence term. And so we're going to try, that ends up being something that tells us about, I guess, the flux on the boundaries and sort of as a way of invoking boundary conditions. So we picked sort of a not really fancy version of the advection diffusion. So we've got a non-compressible fluid, and this diffusion coefficient or function is just a constant. In this case, we're going to have a closed system. So this variable P that we're solving for, maybe it's like the concentration of salt in the water or something. We're going to have the flux of that on the boundary is equal to 0. So nothing leaves or comes into the system. That's sort of the natural boundary condition for this.
Hi, Dev. Hey, Dev.
Yep.
I think the DC one, there's a couple of tricks for the weak form. And I think you need to do an integration by part.
I totally do that.
Did you? Oh, so you did it. And then I thought like that's a little bit what you were doing in the code, and the equation wasn't quite matching. So what you're doing in the code is more like a finite difference.
Yeah, yeah.
So it's not like we're not going to use so the whole idea about the weak form, there's only one like a differential operator. So here in this case is a divergence. So we're not using quite gradient. So gradient is like a divergence transpose and some sort of Mace matrix. So there's a little bit of detail about that. I can help later.
Yeah, that would be good.
Yeah, I think I'm sure I have some notes. So I think that'll be nicer because it's not like not really one-to-one at the moment. So looks good though. Yeah.
Yeah, I guess it's just some of that stuff. Yeah, I found it a bit confusing that you take the weak form and you get this, you get these inner products, and then you have something that says like the gradient on P, but somehow it's divergence transpose instead of being
right. So yeah,
and I know that you can go with the transpose of the gradient, and it's a divergence operator.
Right.
But that justification hasn't been very obvious for some things.
Right. So if you actually write down the equation and then kind of trying to solve the integration part, it's actually getting clearer. So I can help that.
Okay. Yeah. I'm not sure where it got sort of buggered, but I mean, I did take the inner product. I used trig identities, and then you get this. I did use the divergence theorem. Seems like pretty standard practice when doing this. And because the flux leaving or coming into my system is 0, I was under the impression that this term is 0.
Well, what you've done is there's nothing wrong, but but it's not like one-to-one. So one is finite volume, the other is finite difference.
I guess I thought finite difference was, you basically, you look at your PDE and then you just said, okay, this is a differential operator. I'm going to put in a discrete differential operator. And then in some ways you almost add the boundary conditions after the fact.
No, I think the fundamental idea is whether you integrate or not. So if you look at your code, there's no integration part, right? So it's like we can talk about that later. I think that's too much detail. Let's
sure. I mean, I guess the volume terms are in there. I was sort of under the impression that I was actually integrating this over each cell. I mean, yeah, I think you're more knowledgeable than I am, and we can discuss it. But anyway,
no worries. Yeah, I got it. What you did it. So yeah, you're right. But yeah, I have a couple of comments, so we can talk about it later. Yeah.
Yeah. So whatever way I ended up doing it, we got some matrices that look like this, and then I decided to use backward Euler.
Nice.
And so we did the 2D problem, and in the end, it looked like it was pretty legit. So we've got a couple sources, and at early times, it's all kind of concentrated around the sources. And yeah, so we have a velocity field that's going to the bottom right. So you can actually see that the material is diffusing and that it wants to go to the bottom right. And at the source that's in the bottom right, when it hits the boundary, I'm hoping you can kind of see that it's collecting there because it can't leave, because the boundary condition says that there's no flux that can leave or enter the system. So I don't think visually it's the best plot, but at first glance, it looked like it was doing what it was supposed to.
But are you putting like two sources?
Yeah.
Okay.
Yeah. One source in the top right, and then one source in the bottom right. So one thing was just to show we're getting diffusion, and we're also getting this advection going to the bottom right. And then another thing I wanted to show is that we actually did invoke boundary conditions, and that we are getting sort of a collection of material in the bottom right corner because it can't leave.
Devin, if you show this simulation for another 10 or 20 seconds or so, would there be more material that collects in the bottom right? or is it already at steady state by 5 seconds?
I still have to play around with it a bit more because I'm not very knowledgeable in fluid dynamics. So I was really just kind of trying to pick some constants that kind of made the pictures look how I wanted it. So like I don't know what the time scales and like what my time stepping should be. It was sort of a quick example just to show the solution of the equation.
Yeah.
Like
Yeah.
Can you take your system and easily, extend the mesh? Can you do a variable tensor mesh to have, padding cells around the whole thing and then do it again and then see what happens?
Yeah, I mean, this whole thing ran in 0.6 seconds, so we'd be able to play around with this pretty quickly. I mean, I picked a 2D example, so it would be very fast to run.
Nice.
Yeah, but I think maybe one of the steps I think I skipped or didn't do as well with the finite volume is you solve the problem on one cell and then you extend it to the entire mesh. And I think maybe I skipped over that solving for one cell part first and kind of just, yeah.
That's why we do it in team, man. Someone else will look at it. That's all good. You had to start. That's great. Looks good.
Yeah, but that's basically it. So, I mean, I have some stuff that maybe I'd like to talk to Saki and Lindsay about in terms of the process of adding new examples, because we'd like to encourage people to add stuff, but if it breaks the generation of the website and master is broken, and then anytime you go and branch off of master, that's broken, it leads to problems. It leads to some problems.
Right.
And there's still some basic functionality in discretize that hasn't been put in. We can put in Neumann boundary conditions for tensor meshes, but I don't think we're able to put Neumann boundary conditions for tree meshes yet. Or maybe we do it in 3D but not in 2D, because I wanted to do one of these examples. I wanted to not just do all the examples on tensor meshes. I wanted to mix it up a bit.
So that part I can help because the natural boundary condition changes depending upon where you define where do you define your potential, for instance. So if you are using a nodal gradient, natural boundary condition is actually Neumann. So that's how we're doing a DC. So we're basically using like a solving nodal problem to set up the Neumann boundary condition for DC problem, for instance. So if you have an idea and I can definitely help. So let me know if you have some kind of idea of extension or what's missing.
Well, I guess I just wanted to know, were we designing this package to be like something kind of more specifically tailored to us doing EM problems, or was the vision of this particular package like a general, like a way that we can solve general PDEs using finite volume? Because we've defined a curl operator that goes from edges to faces, because that's what we need to solve our EM problems. But we haven't defined a curl operator that goes from faces to edges, unless you count using the transpose. Like there's.
I think it's just because no one needed to use it, but I think eventually we'll want to have them all. Yeah.
Yeah, because I understand that there's like natural. I understand that each differential operator, whether or not you're going from like nodes to edges or edges to nodes or whatever it is, there is kind of like a natural boundary condition that you can put in each of those using the ghost points. But that list of all the operators that map between all of the different places and having all of the boundary conditions, like that, it's an incomplete list. Right now, we got everything we need to solve EM problems, but like I wanted to do something with a nodal Laplacian, and we don't have it tested. And
we'll get there, man.
yeah, so that was kind of a thing.
Yeah.
Yeah.
Sounds good. Sounds good. Yeah, that's great. Dev, I need to go, but I'll take a look and give you a little bit of notes for a DC problem first.
Yeah, I
And,
did look at pixels and where they live. Like I looked at that leading edge article and stuff.
Right.
But
Yeah, I can give you a little bit of note and a snippet of code how I would do. That might help, I guess.
So before you run off, there's one thing I wanted to bring up here, and that is the IUGG.
Right.
So when is your presentation?
I think it's 15th, I guess. I'm pretty sure it was 15th.
And in what session is it? Is it a
It's in a mineral mining geophysics, I think.
okay? And then Tibo, when is yours?
13.
13. That's early. Dom, you were when?
16th, I believe.
Okay.
Let me double check that. Yeah.
I was talking to Lindsay, and we're wondering about the potential for spending a day after the IUGG, because during the days everybody's got their own agenda. But to have one day after where we just talk about SimPEG and really try to outline a roadmap of where we want to go,
Right.
what we're going to need to try to get there, and just use this opportunity that we're all together and try to create a game plan.
Right. So that's what time? Do you know what day? Do you know what day? Do you know what day is that?
Well, I'm not sure. I was wondering about maybe the 18th. I think Lindsay is on the 17th, but I'm not sure.
Okay.
I found that the most obscure website for trying to match up dates when people are actually giving a talk and the session. I still can't find out which days particular session.
I think they don't have a full program. They don't have a full program out yet.
Oh, I guess that's the reason.
So like we know our days just because we got it in our emails, but that's it.
Yeah, I'm on the 16th. Yeah.
Yeah, so it could be either 17th or 18th.
I don't think I could make it the 18th. If we can make it the 17th, that would be better for me.
Okay.
Sure, that's Friday.
So I'll contact Lenny. Let's try for the 17th then.
Sounds great, Doug.
Okay. And then we need to think about accommodations and stuff. I'm not sure we can try to stay together, or everybody just get their own hotel room, or what. But let's at least think about it.
Yeah.
Sounds good. Yeah, so I'm gonna go with Angela. So, yeah, I might get our own place, I guess.
Okay.
Yeah. I don't know how easy that will be if we all together like to share some things between universities. I don't know how that works. Just wondering.
John, what's your thoughts about?
I have friends. I have lots of friends. I can sleep at their places, so don't worry about me.
So that sounds like we'll not bother thinking about an Airbnb this time, with everybody kind of be on their own.
Yeah.
Okay, that sounds good.
You can have your favorite. You can have Lindsay.
Okay. I need to go. I'll see you guys later.
Okay.
Bye,
By the way, Doug, thanks for the bug. I got one, so thank you very much.
Thanks for what?
Bug.
Oh, okay. Good. Good. Bye, Sagi.
Bye.
All right. But yeah, that's basically everything that I wanted to go over.
That's good, yeah.
Yeah.
That'll work.
Good. And I think the important part here is that we kind of go from A to Z here, and that one of the most important parts is that you actually identify places where you're a little unsure about, rather than like, okay, guys, here it is. bring it up, let's make sure we kind of got two sets of eyes on those things, so that we can then put check marks on and go ahead, so.
Yeah, I'm thinking, maybe what Soggy was getting at was, we have this module called the inner product, where it basically will boil take something like this, and it will give you sort of the mass matrix that you're supposed to get from that to numerically evaluate the inner product on a single cell and then extend it to all cells. So it's sort of, I think it's this step right here that he's sort of talking about, and I kind of see where he's going with it, and it ties into how discretize is built.
So let's make sure that we've got all those things flushed out properly. But I think that the thing that I really like about what you've done is that, okay, you've kind of gone from A to Z, and we've got pictures of what's there, we've got mathematics, and now people can look at it. They can look at the whole thing, and they can either say, yeah, that looks a little bit strange, I'm going to investigate that more, or that's good, I'm going to adopt it, and off I go. So, yeah, 2 thumbs up.
Yay!
Okay.
Sweet.
I have not got to the paper yet, but I plan to do that soon, within the next
Let's
day or
stop
two.
the
So,
broadcast.
Did you say you did?
Yeah, I combined those two papers, I combined them.
And
Now we have just one paper.
I think that sounds good.
I
Where,
will show
Did you
you
send
whenever
me-
you are free, I'm not in hurry.
it's on my list, but last week